Welcome to video clip 3.3, in which we explain soundness. So the idea of soundness we discussed in the previous video clip already. Now we make it a bit more concrete and we identify 3 properties that are important, that need to be fulfilled for a process model to be sound. We assume process models to be structurally sound. So soundness has these 3 properties. 1, once a process has started, regardless of which decisions are taken by the process, at some point the process will reach the end event O. Property 2, if and when it reaches the end event O, the process has completely terminated, which means no further activities can be executed by the process anymore. And the third property is each process activity participates in at least one execution, so is present in at least one trace. We will apply soundness in the next slides. Before that, I'd like to make this remark that soundness is a generic correctness criterion, which is quite similar to normal forms in databases. Some of you might know normal forms in databases that are properties of database schemas that avoid certain behavior or certain data content in the database that is not useful. So it's quite similar to that in the sense that we can show a property on the model level, and then on the instance level, so each process instance, we can be sure that that the property holds for all of these instances. So I only need to show the property once for the process model, and then I don't need to check each process instance if it complies or if it is sound. We can deduce that it is automatically sound if the process model is sound. And that's also similar to what we see in databases, where if we can show that that the database schema is in a certain normal form, then certain anomalies cannot occur in the database. All right, so let's look at the 3 properties. Properties 1, 2, and 3 by example. And though the first property was, regardless of which activity or which decision is taken, the process eventually reaches the final event, the output event. And let's see if we can do a brief analysis here. We can decide to work here or here or here. In any case, at some point we are at the point of decide on claim coverage. Yeah? Regardless of which of the 3 decisions are taken, I will always come to the decide on claim coverage. And then I can either work here or there, but in any case, I will come to the output O. So all behavior, regardless of which decision is taken by the process, I come from the, we say, state, the initial state to the final state, so from state I to the state O. So property 1 is obviously met. Property 2, if I reach, or O is the only state in which, or if I reach the final state O, if I come to the O, then the process model is completely terminated. So there's no more activity happening there. And also we can see this basically by the same walkthrough I did before. So when I come to the claim processed, when the claim processed event occurs, then I can be sure that no other activity is still happening. There's no activity left in the process. And the third example, or the third property is that all activities can participate in this process. Of course, that is also true, and that's also shown in the walkthrough. You see here that the yellow lines are everywhere, so all activities can happen. Not all activities need to happen, and all events need to happen for the same process instance, but for, let's say, all activities are in one trace. And by the way, each trace that we produce here starts with I and ends with O. So that's also a nice application of what we learned about traces before. Formally, the process is in a deadlock after O has been reached. So a deadlock is a situation in which a process cannot move further, or in general a system cannot move further, it got stuck. And of course this also happens here when O occurs, but at that point it's perfectly okay, because at that point the process the process does not need to continue, and therefore the deadlock in state O is perfectly okay, and and it does not violate soundness. Okay, so once we know what sound behavior is, how can we detect unsound behavior? Well, by negating either of the three properties. So we can detect unsound process behavior by finding a violation of either of the soundness properties. So violation of property 1, the process cannot reach the final event O, it gets stuck before. There's a deadlock, and the deadlock before O is reached, to be precise here. Violation of property 2 means remaining activity. There is remaining activity in the process after reaching the final event. So the final event is reached, and still activities can happen in the process. And we even see an example where there's a continuous execution of activities after the final event, output event has occurred, and that's called a lifelock situation. And violation of property 3 is that there might be activities that can never be executed. These are called dead activities because they appear in no trace of the process model. Therefore, we would also say this is unsound process behavior. So let's look at the violation of property 1. It's a deadlock violation. We look at the example that we introduced in the previous video clip. So you remember the problem that we had here. So first of all, we make another walkthrough. So here we have the concurrency. So after receive order, these two branches can be executed independently from each other. And here then is a synchronizing join. The end join synchronize the two branches, check payment is done, the payment is okay, and then O is reached. Yeah, so of course here we have the event I, and here we have the event O. All right, so that's an example of a completely valid execution of this process model, and so there's no problem here. However, property 1 states that regardless of the decision taken by the process, the property should hold that I reach O. So let's see what happens if I erase that again. What happens if I did these things the first time, but then this decision is taken, invalid amount, send update invoice is performed, receive payment is done twice, and then the process is stuck. So here the process is stuck because the end join cannot fire. And in this case, the O is not reached, so the final event O is not reached. So there are decisions in which the final event is not reached, and therefore the process model violates property 1. Violation of property 2, remaining activities or lifelock. Here we have a lifelock. If and when the process reaches O, it has completely terminated. No further activities can be executed by the process anymore. That's a property 2. Here we have a slight change. So maybe some of you spotted the change of the process model already. And that is, we have here we have an XOR join, and here we have an AND split. Okay. So what happens is that receive order, here we have the AND split, the XOR join immediately triggers the outgoing add, check payment is done. Here the first time O is executed, but here we have the send updated invoice. Then we have from the first iteration, we go here, we have the check payment, and here we have another iteration and receive payment is done. So this loop will continue without any end. So that's a lifelock consisting of these three activities, because the problem is that, of course, this is an AND split. And in order to avoid the deadlock here, we introduced this XOR join, which leads to a consecutive or to an infinite, let's say, execution also of check payment. All right, that's an example of a lifelock, also something you would not like to see in your process. By the way, also this is a perfectly legal process model in terms of syntax. It's even structurally sound, but still it has these behavioral anomalies that are incurred by the wrong use on the wrong use of the gateways and also of the structure. Okay, a process is in a live lock if the control flow structure makes the process executing an infinite number of activities. We have seen this in the previous slide already, so here we can have a dedicated explanation of the live lock. But it does not only need to be a live lock that violates property 2, but we can also have remaining activity in the process. So after reaching the final event, there might be additional activities happening in the process. And an example that we see here and that we also see in real-world process models here and there, if we use an AND split and if the AND split is then closed with an XOR join. So what happens here is that we receive order as the first activity, then we package the product, and these again concurrency introduced by the AND split, issue payment, receive payment. If receive payment completes, check payment is done. And if issue shipment is performed, check payment is done again. After the first execution of check payment, the end event occurs, but then check payment can still be executed. Or depending on the speed of the concurrent branches, even more activities can be executed. So let's look at that maybe in more detail. So let's assume receive order is performed, send invoice is performed, receive payment is performed, the XOR join is performed, check payment is performed, and the end event occurs for the first time. So that should signal the end of the process, but there is no end of the process because packaged products can be executed and issue shipment can be executed and check payment can be executed one more time. So reaching the final event O does not signal the end of the process, but there's activity left, and these activities are called, or this is called, the situation is called remaining activity after reaching the final event. How to avoid unsound processes? Well, we could always use structured process models so that each split is then closed by the respective join. So each split gateway has exactly one join gateway of the same type, so that each path originating from the split will reach the join. So that's a block structured model. We also say block structured model to this structure. This makes sure that loops obey, or this makes also sure that loops obey the block structure, and as seen in the earlier example. However, using only block-structured process models limit the expressiveness, so you are limited in what you like to express. For instance, you cannot express the different outcomes. You cannot express that you have an XOR split, so either yes, the order is fulfilled, or no, the order is not fulfilled. And you cannot use different end events to represent these two different outcomes, so there's a limitation. So in general, it might not be so a good idea to use only the structured process models. Okay, we sketch that in the middle part here. However, these constraints limit the possibilities of modeling. Process models that are best understood might not be possible. So there's a price to pay, and the price to pay might be quite high in many cases. But there is a better way, and the better way is you use smart modeling tools, and there are modeling tools like the Signavio process editor that you have been working with. So you use smart modeling tools that provide soundness checks and feedback messages on why a given process is not sound. So that's always a good way to use these formal properties and to be able to check these properties also in your modeling tool. That concludes video clip 3.3, in which we explained soundness. So soundness, the idea of soundness is that every process instance terminates properly. So in any case, regardless of which decision is taken by the process, I reach the final event O. If I reach the final event O, there is no more activity left in the process, and all activities contribute to at least one process instance. we saw a number of violations. So in order to detect unsound behavior, we can look for deadlocks, we can look for live logs, or we can look for remaining activities. And structured process models actually help avoid these anomalies. But there's a price to pay, and also there's a possibility of using the right modeling tool. Then you can model as you like, be expressive as you like, and still be sure that your process does not have behavioral anomalies.